Now I'm going to show you about maple and graphing vector valued functions. First off, in the first part of this, you won't be graphing the things the same way I am. I'm using the actual vectors to illustrate the relationship between a vector valued function and the associated vectors described by that. So I'm going to start here with some two-dimensional graphs, and I've got the vector valued function that you see here, 5 cosine t squared, 5 minus the square root of t. This is actually a problem out of the textbook. And so I'm drawing the vectors for each value of t that's being used to construct the graph of the vector valued function. And so let me show you the animation for this. If you start with the value t equals 0 and then increase that, here's t equals 0.26, you see the curve in red being drawn by the vectors. And so this vector valued function creates a curve, the red graph, and it's the blue vectors that trace out or create the curve. And so I'll run this through and then run it again so that you'll see here's how it's traced. We'll slow it down some and run it again so you'll see how it's traced. And again, the end result is the red graph. Here's another function. You can see here what the function is. Again, this is out of the textbook. And here's the animation for that function. Here's the vectors drawing out the graph. And again, one more time slower. And these are problems that I've taken from the Section 1 exercises. Here's another two-dimensional graph. And here is what the graph looks like when we trace it. And here's the last two-dimensional one we'll take a look at. I've made this one up myself. It's not in the problem set in the book, but you can see the graph of this. Now the vector is long and skinny because maple defaults to using a width that is proportional to the length, and these particular vectors are very long, and I didn't take the time to scale them. And the neat thing is the same thing occurs in 3 dimensions. So if we have a vector valued function that has 3 components like you see here, we use exactly the same technique for graphing. And again, I'll draw the graph on this one so that you can see the vector is tracing out the graph, and it's 3-dimensional. Here's another 3-dimensional graph, t, 2t, 5 minus e to the negative t. And here's what the graph looks like. And again, we can tilt and turn, and get the other perspectives on the graph. Another three-dimensional graph, you can see the function here. I won't bother reading that. You can look at it and see. However, here's the trace. And here's the last one that we'll take a look at. This is the 4t, t squared, and 5 sine 2t. And here's the function. We'll draw it again. All these documents are available in Maple if you want to experiment with these things. Now to the nitty-gritty of this, we don't particularly care to see the tracing of them all the time, although, again, in vector-valued functions, orientation is a part of the function. It's built in, the direction in which it's being constructed. And so here's the basic command that's used for drawing vector-valued functions. In Maple, we use the command called space curve. Now you can see in the first sentence, there is a space curve command in the plots package. There's also a space curve command in a package called vector calculus. I'll show you how to use these in class. Notice the case, however. The space curve without any capitals comes from the plots package. The space curve with the capital S and the capital C is the command in the vector calculus package. Now that's also available in the student vector calculus package, and the only difference between them is some of the assumptions made in the student vector calculus package means we don't have as much work to do as if we use the vector calculus package. You can see here I've used the capital S space curve, and so this is the one from the vector calculus package. Now if you use that space curve command, the function that you give it here has to have the angled brackets indicating that it's a vector. You cannot have the square brackets. That is not a vector. That's a list. However, again, we get a three-dimensional graph, no indication as to how it was constructed, so we're kind of on our own as far as what the orientation of the graph is. The last topic I want to show you has to do with intersecting surfaces. So here you see the yellow dome looking thing is the top part of an ellipsoid. Here's the equation for the ellipsoid that we talked about in the last chapter. And here is the graph, we did this in the last chapter also, of a parabolic cylinder. And again, you can see its equation here. And so here is the graph of the two together on the same coordinate system. So as you can see, the two surfaces intersect. They intersect in a curve. And our goal is to find and graph the curve of intersection of the two surfaces. Okay, so here's what we're going to do. We're going to start by substituting the parametric form of the parabolic cylinder into the equation of the ellipsoid and solve for z. Now here is where we've done that in Maple. All of that is done in one line. So this x, well, sort of in one line. We had to do some of it in our head. This that you see here is the parametric version of the parabolic cylinder. And so we've taken the parabolic cylinder, which was y equals x squared. We've used a t for the x, which made y a t squared, since y is equal to x squared. So that's how we parameterize the parabolic cylinder. What we're going to do then is substitute that into the equation, that's what EQ1 is, of the ellipsoid. After that gets substituted, we're going to solve that for z. Now you see, when we do that, we actually come up with two values of z. That should make sense. A positive and a negative. And from our picture, we can tell, since it's above the xy plane, that we want the positive one. And so this would be our value of z and x and y. So here is our vector valued function that represents the curve of intersection. Again, the t is the x, the t squared the y, and then what we just solved for is the z component. Now I've drawn the graph of those so that you can see the red line is the curve that we just found. So the two surfaces along with the curve. You can see it is indeed the curve of intersection. But of course, eventually we're only interested in the curve of intersection. So there is what we just came up with, the intersection of those two surfaces.